And so we find ourselves on page 178, and we're going to make the second transition now when dealing with absolute values. We looked at expressions individually. Now we're going to put expressions together on either side of an equal sign and create equations. And of course, before we go too deeply in this, we'll do a couple of warm-up questions. Well, there's one good warm-up question here just to remind us of what we're doing. So let's jump right into this. We are on page 178, and as a warm-up, we're going to take a look at the absolute value function, the form f of x, or y, equals x squared plus bx plus c, where b is not equal to 0, c is not equal to 0, so b and c are not 0, and c are members of the real numbers. Okay, cool. F of x has a domain of all the reals, that's good, and a range of y greater than or equal to 0. Now, so let's just think about this for a second, shall we? If we're looking at and talking about a quadratic, so a parabola, with a domain of greater than or equal to 0, then that means that everything is in the y direction is between y equals 0 and up. There's nothing below the x-axis. There are no negative y values on this function and on this graph. So we know that everything after the absolute value transformation is kicked in will be above and stay above the x-axis. So it'll be interesting to see how this parabola plays out, because it could be something like that, because that would naturally stay above there. But if the parabola dips down below the x-axis, you also know that because we're applying an absolute value function to it, that this is going to pop up like that, and so everything will be fine as well in the mix. So just some things to keep in mind about before we actually jump into this. So what information do we know? What can we use? And all of that. So let's begin with some known things. We know these intercepts here. We know that there's x-intercepts at x equals -6 and +2. And we also know that a point, well, we know a couple of points. We know that these 2 points here are on the graph, but we're given a third point as well. And let's use that because it'll be a little bit more straightforward. We know a point 0, 12 lies on the curve. We know a couple of things that will allow us to start building the formula for the quadratic. Y is going to be equal to a times, and then if we have the intercepts and we have the zeros, and so we can start building an equation that looks like this. And yep, and we're taking the absolute value of that. But we also know that because this point is on the curve, that we can substitute 0 for x and 12 for y. So let's go ahead and do that now. We'll have 12 equals the absolute value of a. So 0 plus 6 times 0 minus 2. Cool. And when we sort this out, a times, let's see, 6 times -2 is -12. And what this is going to give us now, if we're trying to figure out what the a value, which is the purpose of this whole part of the problem, a would equal, well, plus or minus 1. And we don't know which one it is because when you take the absolute value of it, you lose that information. So you can imagine a would be -1, and -1 times -12 would be +12, and the absolute value of that is just 12. But you can imagine a situation where a is just positive, some positive value. And positive times -12, even if it was 1, positive 1 times -12 would be -12, and the absolute value of -12 would be 12, and we're right back to the same thing. So a can be either positive or -1. But the interesting thing about this, though, is that in this case, a can only be positive because we're looking at the absolute value of the entire function right there. In this case, a must be greater than 0 because of the absolute value function. And so therefore, a must equal to +1. And now if we substitute that information in, we've got back again to the original question right here. What is f of x of the square root? We want the values of b and c, which means that we are looking for this number and this number. It's not asking for a, even though we have to calculate it in order to determine b and c, but no, we have it anyways. So let's expand. Let's expand. Let's take f of x, absolute value of 1. We don't need to put the 1 there, but I just want to show you where the a value comes from. And we'll take the expression x plus 6, x minus 2, and what we'll do is we'll simply expand it. All right. And so it's going to become the absolute value. Now I'm going to take away the 1 or ignore the 1 because it's implicit in the expression. X plus 6 times x minus 2 is going to be what? X squared minus 2x plus 6x, so plus 4x, and minus 12. Cool. And so now we can very easily and quickly read off the a and the b and c values. A, it's not asking us for a, but let's put it down anyways. B would be 4, and c would equal to 12. All right, and so there we have taken a really good review of a lot of the stuff we've done in the quadratics unit, and you can see how now we're using that stuff that we learned a few months ago in factoring and expanding quadratics and what they mean and what zeros mean and what roots mean, and using them now in the context of absolute values. Now the next key insight will be, well, why are we doing absolute values at all? And I'm afraid I can't really explain that to you with much meaning until you get to next year into Math 30-1, but especially Math 31 Calculus. So moving right along here, let's move to a couple of graphical examples of equalities and equations and see what it is that this all means. Questions like this are asking, what are the points of intersection? What are the solutions to these? And if you need a little bit of a reminder of how these kinds of systems work, you need to recall that hidden inside of here are actually two lines. There's a line, and let's call it y1, of y equals the absolute value of 6 minus x. And then there's another line on the other side of the equal sign. Let's call it very cleverly y2. And y2 is simply equal to 2. And y2, I think, is probably the easiest one. It's just a straight line across with the y-intercept of 2 parallel to the x-axis. But when we're talking about the absolute value of 6 minus x, there's two ways of looking at it. Now, in the olden days, if we did a line and a line, there was only one point of intersection. Sometimes there could be, remember when you have a system of linear equations, you can have one solution, you can have zero solutions if the lines are parallel, and you can have infinite solutions if they're coincident, that is, if they lie right on top of each other. But now, because of this absolute value, we have something that looks like that. All right, and then with a line coming through it, we're going to have two different solutions. All right, and what are the options here? Well, we could have two solutions. Could we ever possibly have one solution? Well, sure. What about a line that came like that? Okay, there's only one solution, and because these lines diverge above the x-axis, they'll never meet above the x-axis. Could we ever have a situation with one solution? Yep, sure can. What if the line is right on the x-axis there? There's one solution. And then plenty of options and reasons why you'd have a system with no solutions or zero solutions, right? So we've got to try to figure out and get our heads around what's happening here and how many solutions we're dealing with. Now, there's two different ways to look at question number one. And I think I'm going to start off with the easy way. If you look just above here, you read this important piece of information right there, which says that in every situation we're dealing with absolute value equation that we're looking at two cases. So I'm going to do it the way I think you understand absolute functions to work and absolute values of lines to work. And then I'll go back and talk about what we mean by two cases, okay? Let's graph y1 of the absolute value of 6 minus x. Well, 6 minus x is the same thing as I think you'll appreciate negative x plus 6. And we are taking the absolute value of that. So we'll keep that in place there, okay? And so what do you notice about that equation or line? Well, if it was just y1 equals negative x plus 6, then you know it's got a negative slope, and so it slopes downward from left to right. You know that it's got a slope of 1, so over 1, up 1, and so on. And you know it has a y-intercept of 6, right? So let's start by drawing what we know. We know it has a negative slope and a negative slope of 1, so it's going to hit all of these diagonal cross points here. Over 1, down 1, over 1, down 1, or left 1, up 1, left 1, up 2. Now, because you know that we're dealing with an absolute value, you know that there's a turning point at x equals 6, and that's going to make the graph look more like that, right? So you know that rotation of the bottom half of that line up and over. And so I'll erase this because we don't need that anymore, and we'll just draw the line as it was. All right, so there's our absolute value graph of 6 minus x, or as I rewrote it, negative x plus 6. Don't be afraid of changing equations and expressions around to fit the normal pattern that you expect when you're talking about equations of lines or equations of parabolas and so forth, okay? All right, so we've graphed y1, which is negative x plus 6, and we have taken the absolute value, so you've got y equals 2, y equals 2. And I think we've gone through this already. It's a horizontal line parallel to the x-axis with a y-intercept of 2. And because we're solving this question graphically, you can just take a look directly at your graph and you can see the two solutions. There's a solution at, or an intersection at 4 comma 2, and there's an intersection at 8 comma 2. Label this as a solution of x values that include the set 4 comma 8. And if you even excluded this, you wouldn't even need to write that because it's the only possible values that we're solving for. All right, so what do we mean then? I promised to come back to this. What do we mean by saying that there are two cases? Well, what we mean is this. For the graph, absolute value is 6 minus x. There are actually two possible values that can come out of that. The first one is if 6 minus x is greater than 0. That is, if it's naturally positive. And if it's naturally positive, you get a line that looks like this, don't you? Okay. But the other case you get is if 6 minus x is negative. In other words, it looks like that. And in this case, if we just expand the negative 1 through, we're actually going to get x minus 6, a line with a positive slope and a y-intercept of negative 6. It's going to cross the y-axis down here. And that line would look like this. So this is the definition of why we get two solutions, because there's two possible lines that fit the situation we've got. We have the situation where the equation is already greater than 0, and we have the situation where the insides of the absolute value were negative and turned into a positive u. So there's always going to be two cases. So later on, when the questions get a little bit more complicated and we talk about case 1 and case 2, this is what we're talking about. So let's turn our attention to the next question here, question 2. It's a little bit more complicated, and I'm going to do not a trick, but it's something related to the relationship between this and this. Now, both of those look similar, right? And the only difference is the quantity squared value in the first example. But you might recognize, especially if I do that, you might recognize the top version of being the equation of a parabola or a quadratic in vertex form. And you're able to determine the vertex, first of all, of 2 comma 5. But more importantly, you're able to identify this as having had the original curve shifted to the right and 5 up. There's 2 to the right, and there's 5 up. So could there possibly be an analog to x minus 2 quantity plus 5? Could that also mean shifted 2 to the right and 5 up? And what's the difference between x minus 2 quantity plus 5 and, say, x plus 3? Or is there any difference? These are interesting things, and if you really understand what's happening with transformations, then this will become immediately apparent. This is a straight line that has been shifted over and up. I'm going to show you how that works right now. All right, let's play the transformation game. I want you to recall that we are actually graphing two lines here. We're graphing this part here, which is the negative absolute value of negative 2 plus 5. And you haven't seen a negative absolute value. And I think maybe if you think about it, the answer to what that looks like could be intuitive. But in addition, we also are going to graph this line here, the absolute value of x plus 1, which is traditional, and you've seen that a couple times already. We're going to treat this whole thing here as the transformation of a line that goes through the origin with a slope of 1. So we're going to treat it as a transformation of y equals x. And there are going to be 4 different things we do to this y equals x equation to get us the y equals negative absolute value of x minus 2 plus 5. So I'll do this step by step. First of all, we're always starting with a line of y equals x. Okay, that's your basic line, and it's going to look something like this. There's y equals x. Now the first transformation I'm going to apply, and I can apply these 4 transformations in any order I want because the one does not depend on the other. But I'm going to do it in the simplest way so that you can see obviously how things are working. The first thing I'm going to do is I'm going to take the minus 2 translation. Now, if we're looking at an equation of a parabola that looked like this, then we know that this gives us a rightwards translation of the curve plus 2 in the x direction. This is no different. This is the same thing. We have a 2 plus 2 translation of the line in the x direction. And so it's going to look like this. And if you think of what we've done, we've translated every point on lilac 2 to the right. So we'll use 0, 0, the origin, because that's a good one to start with. We've gone 2 to the right. So 0, 0 becomes 2 comma 0. All right. So that's the first translation we've done. Y now equals x minus 2. And you can see when we're graphing a line, if it was just a straight up line, y equals x minus 2, you see that it has a y-intercept of negative 2. And now you see where that comes from. But now you also see the reason we can say that the y-intercept is negative 2, because we've actually moved the whole line over by 2 in the positive x direction. The next thing we're going to do, just because it's easier to do it now than later, is we're going to take the absolute value of that line. So we're going to take y equals the absolute value of x minus 2. And you know now that what it means is that at this turning point, the graph is going to start flipping the other direction like this. So there's the second transformation we've done. Nothing happens, notice, to the turning point. That it's not really called a vertex, but you can, well, it is a vertex, but it's not the vertex in the sense of parabolas, or maybe it is. Maybe it is. But notice that when you take the absolute value of a function, that vertex point doesn't change at all. That turning point stays the same. It's called a turning point because everything turns around it. This is really what happened there, right? That bottom part of the blue graph that had values of y less than 0 now become greater than 0. That gets reflected about the x-axis. All right, cool. Now, the next step I'm going to do, I think, because it makes it makes sense to do it now, and I think you'll understand it better, is we're going to take now the negative absolute value of x minus 2. We're going to go y equals negative absolute value of x minus 2. What does that do? What does multiplying by negative 1 have to do? Well, it means that now instead of all values being in the positive y direction, they all get flipped in the negative y direction. It's a reflection about the x-axis. That's what multiplying by -1 does. It reflects it back around the x-axis. And so now that's going to look something pretty close to that. All right. So we've had 1, 2, 3 transformations, 1 transformation left for us to do, and that is for +5. And if you recall from the vertex form of a quadratic, what the +5 does in a similar situation, if this was x minus 2 quantity squared plus 5, this shifts the graph upwards in the y direction, in the positive y direction, by 5. Recall that our reference point was 0, 0. The first transformation brought it to 2, 0. The second transformation, the absolute value, did nothing to it. The third transformation is going to move it up 1, 2, 3, 4, 5 to there, so that everything gets shifted up and it's going to look like this. Just a reminder of what we did. Y now becomes the negative absolute value of x minus 2 plus 5. Boom, just like that. Again, if you think about all the parts of the right side of the equal sign, consider it to be a line undergoing 4 distinct transformations. You can go from a positively sloped line through the origin with a slope of 1 to what you see in purple pretty easily. So now what I'm going to do is I'm going to unclutter the graph a little bit by getting rid of all the old stuff that we don't need anymore. Okay, this is the first half of our graph. So if you recall what we're doing, and the purpose of this whole exercise is to find the intersections of y1 equals that, and the cleverly named y2, which is this, then you know that we have to graph. So we have to now graph y2, and hopefully they intersect somewhere. So now we're going to graph y2 and see if and where they intersect with line 1. So y2. So y2 is the absolute value of x plus 1. Now, if we were just doing x plus 1, then it would have had a x-intercept at -1 and a positive slope of 1, which would look like that. Now, because it's the absolute value, it's going to look a little different. We know where the turning point of the absolute value function is. It's going to be the x-intercept, one of those most important invariant points of any absolute function graph. And instead of a positive slope of 1, it's now going to have a negative slope of 1. And instead of a y-intercept of positive 1, it's going to have a y-intercept of -1. So it's going to look like this. And so there's the piecewise function of y2 with x equals -1 being the turning point. And now it's a very simple matter to identify the solutions graphically just by noting where the intercept points are. There are 2 interceptions at -2, 1 and at 3, 4. And so our solution then becomes x equals set of numbers that include -2 and 4. All right, so we're sticking with linear equations, okay, systems of linear equations. And back up here, we talked about the idea that there are 2 cases. Now, when you're doing and solving a question graphically, those 2 cases might not be immediately apparent. Well, in question 1, I actually drew them. Case 1 is green, case 2 is blue. But when you're solving algebraically, you're going to have to be a little bit more explicit about what your cases are. So what I mean by that is this. For x plus 5, there is a situation in which case the whole thing could be positive, and taking the absolute value of it has no effect. In other words, x plus 5 is just x plus 5 as long as x is greater than or equal to 5. For all values of x 5 or greater, you're going to naturally get a positive value to the term inside the absolute value symbol. But the other case that we're going to deal with now is if x is less than 5. And if x is less than 5, and we're going to get the negative of the stuff inside the absolute value sign, right? Because the definition of an absolute value is positive whenever the insides are positive anyways, but negative the insides if the insides are negative. So when I distribute the negative 1 over the x minus 5, I'm going to get negative x minus 5 for x less than 5. All right. So let's solve these. If the absolute value of x plus 5 is naturally positive, that is for values of x greater than or equal to 5, then the equation becomes this: x plus 5 equals 4x minus 1. And a little bit of simple algebra, I think, will do this to you. Good. Boom. That's pretty simple, straightforward, done. Let's now look at what happens when x values are less than 5. When x values are less than x and 5, then the insides of the absolute value we're dealing with are negative x minus 5 equals 4x minus 1. And when I move this around, I'm going to get 5x equals negative 4, and x is going to be equal to negative 4/5. So here we go. We've got two solutions, and we should probably confirm and make sure that these are actually real solutions and not extraneous roots or extraneous solutions. So let's do that. Let's verify one, and we're going to verify it by plugging x equals 2 into the original equation. Instead of x, of course, we're going to use 2. All right, so 2 plus 5 is 7. The absolute value of 7 is 7. And on the right side, we're going to add 4 times 2 is 8, minus 1 is 7. Yep. All right, so it looks like x equals 2 is a solution. Let's now do the same thing with x equals negative 4/5. Okay, and we're going to do that just by, again, plugging it into the original equation. So we're going to get negative 4/5 plus 5 equals 4 times negative 4/5 minus 1. All right. So before we do much here, let's just see if we can suss this out logically. On the left side, because of the absolute value, we're going to get positive, because anything inside that absolute value, if it were negative, it would be transformed by dropping the negative, okay? On the right side, you have a negative minus a negative, which will make it even more negative, times 4, which would make it even more negative. So we know just by inspection that the right side will not equal the left side. Now you can go ahead and do the math if you want by continuing the plug-inage. Negative 4/5 plus 25/5 is going to be what? Negative 24/5, but the absolute value of that is going to be 21/5. I mean, you can work through the math, but I'm telling you, you don't have to, because you can tell right now by inspection that the left-hand side will not equal the right-hand side, and therefore negative 4/5 is not a solution. So to summarize, the solution then is x equals to the set of numbers that includes 2 and nothing else. Okay, there we go. We have successfully solved a more complicated piecewise absolute value equation. And now you see very clearly how there are two different options that you have to choose from. Let's try the next question there and see if it works the same way. Pro tip, it does. All right, we have the absolute value of 4x minus 5 plus 9 equals 2. So let's try to figure stuff out. So remember that with an absolute value, we're dealing with two cases. So let's cleverly call it case 1, in which 4x minus 5 is inherently positive, and so plus 9 will equal to 2. And then let's deal with or think about the second case, in which the 4x minus 5 turns out to be negative, but the absolute value turns it into a positive. So negative of 4x minus 5 plus 9 equals 2. In the first case, we've got 4x minus 5 plus 9 equals 2. And what are we going to get here? Let's get the 4x, leave the 4x. And on the right side, we're going to have looks like minus 2, and x equals to negative 1/2. See how we did? So that's the first case. Let's now go to the second bit here. So if we have negative 4x minus 5 plus 9 equals 2, then what we really have is negative 4x plus 5 plus 9 equals 2. That's the second case. And so we're going to get, let's just keep the negative 4x there, equals, and when I bring that over there, it's going to be minus 12, it looks like, which means that when I set this through here, we're going to get x equals to 3. There's my second solution. And before we get too set in our ways, we should verify that. So I'm already in green. I'm going to plug x into 4x minus 5 plus 9 equals 2. So working this out, we're going to get the absolute value of 4 times 3 minus 5 plus 2 outside the absolute value sign, and then 2. And then working this out, well, 4 times 3 is 12. 12 minus 5 is 7. And the absolute value of positive 7 is just 7. 7 plus 9 equals 2. Whoa, really? 16 equals 2? Nope. So x equals 3 is not appearing to be a solution. Alrighty, well, let's go to the other one. Maybe we'll have a little bit more luck here. We're going to substitute x equals negative 1/2 into the absolute value of 4x minus 5 plus 9 equals 2. What are we going to get? We're going to get the absolute value of 4 times negative 1/2 minus 5 plus 9 equals 2. And 4 times negative 1/2 is negative 2, minus 5 is negative 7. Absolute value of negative 7 is positive. So let's finish this off here. Plus 9 equals 2. 7 plus 9 is 16 equals 2. Nope, that does not appear to be a solution either, so that's not going to work. There appears to be no solution here, even though we got some numbers. You will only know, well, you'll know if you verify, like we've just done, but I want you to look closely the equation we started with right here. Let's do something here. If we start off with that equation and we just did a little bit of algebraic manipulation, we would very quickly get this. 4x minus 5 equals negative 7. Now, as soon as you see that, your spidey senses should be tingling. You should be noticing that on the right side, you have a negative value, but on the left side, you will always have a positive value. So in this case, once again, you can never have an equality. You'll never get a set of solutions like this. And if you were to done that work first, instead of all the stuff you see in gray and green, you would be awarded full marks because you have proven that there are no solutions. Because you have proven that there are no solutions. And that is the whole purpose of this, to show if there are solutions, and if so, what they are. Cool. So you can save yourself a lot of time if you just think ahead a little bit. Okay, hello. This is going to be part 2 of absolute value expressions and equations. I'm sitting here on my front porch in beautiful downtown Inglewood, and I'm going to do a lesson where everybody around me, all my neighbors are going to hear me talking this math talk out loud and look at me crazy. So don't you for a second think that you shouldn't be doing this too one day. If I can do it out here, you can do it over there. So let's get started here. Let's figure out how to share my screen with you. All right, so here we are on page 180, and as promised, we're going to bump it up a notch here. Instead of taking the absolute value of straight lines, we are now going to be talking about the absolute value of quadratics. And that makes things just a little bit trickier, but there's still nothing that you can't handle on this. So just like when taking absolute value functions and graphing the absolute values of lines, there are going to be two cases that we need to think about here, okay? And in the first case, and let's cleverly call it case 1,
we're going to presume that everything inside the absolute value signs are positive. So we're going to presume that x squared minus 3x equals 2. And the second case, which is going to be standard for any kind of question we do with absolute value, is when the negative of the contents inside the absolute value signs, the negative version of that, or the reciprocal, is also equal to. So case 2 then is where negative x squared minus 3x equals to 2, okay? All right, so since I'm in blue, let's deal with case 2 first, for no better reason than I've got the blue pen already selected. Let's figure out what -1 distributed through that all equals. So the first thing I do is drop the brackets, and when I do it, I'm going to get negative x squared plus 3x equals 2. And now let me bring the x squared over and then send it over again. What I mean to say is I'm going to take x squared, because I'm really moving that x squared over, minus 3x plus 2 is going to be equal to 0. And when I present a parabola like that in standard form, you should hopefully be able to see very quickly that I can get x minus 2 times x minus 1 equals to 0. Well, that's really good, because that means that x equals to either 1 or 2. Bingo, we got it. Okay, let's move on then. Let's look at case 1. I've changed my pen color, and let's see what we get out of this here. X squared minus 3x equals 2. I'm going to shift things around a little bit, and I'm going to get x squared minus 3x minus 2 equals 0. And I look at that and I ask myself, is that factorable into integral factors? And you know what? I'm not even sure that that's factorable, right? I don't know what that, I mean, I know what that looks like. It's a parabola. It's an upward opening parabola that you know, I don't know, goes up there somewhere. You know, maybe it goes like that. I just can't tell directly from that. So let's, what can we do? What can we do to figure out if this thing has factors? I know. Do you remember back when we looked at quadratic equations that equal 0, that there was a method to figure out what the x values were? Well, it's called the quadratic formula. And what is it? It's x equals some big mess over another big mess. Negative b plus or minus the square root of something. Square root of b squared minus 4ac, I think that works out, all over 2a, okay? Where a equals 1, b equals -3, and c equals -2. Now, before I go in too deep, is there a way to figure out whether or not there are, in fact, factors? Well, remember when we were talking about the discriminant, right? And what that tells you. If the discriminant is possible, that is, if you don't get a negative number in the discriminant, that means that you have factors. If you get a negative number in the discriminant, it means that there are no real roots. And if you get a 0 in the discriminant, that means you get one root, because it just kisses the graph sort of like that. And it doesn't look like it's kissing the graph, but we're going to pretend that it's kissing the graph. So what does the discriminant tells us? Discriminant says if b squared, which is -3, minus 4 times 1 times -2 is a positive number, then we have roots. 9 minus 4 times 1 is 4, times -2 is -8. So minus and -8 would be +8. And it looks like we have root 17. Oh my gosh, that looks ugly. That's just messy. The good news is that we do have roots. The bad news is that it has a root 17 in it. All right, discriminant test tells us we should move forward. Okay, well, let's finish this off then. So what do we get for x? X equals -b. Well, b is 3, so is -3, so -3 plus or minus, well, we already did the discriminant, so we know it's plus or minus root 17, all divided by 2 times a, which is 1. All right, and it looks like we get x equals 3 plus or minus root 17 over 2. All right, so we've got 4 possible x values. And, well, let's go ahead and do the simple stuff first, okay? What do we do with these x values? We don't know if these are true solutions until we verify. We verify by plugging x equals 1 into the original equation and x equals 2 into the original equation. So let's do verify by subbing x equals 1 into that mess. X equals 1 into the original equation, which was absolute value of x squared minus 3x equals 2. And when we do that, we are going to get 1 squared minus 3 times 1, absolute value equals 2. 1 squared is 1, minus 3 is negative 2, and the absolute value of negative 2 is, of course, 2. So that one works. Good. And now we're also going to verify x equals 2 into the same equation, which is x squared minus 3x equals 2. All right, well, let's do that. Well, we're going to get the absolute value of 2 squared minus 2 times, minus 3 times 2. Absolute value equals 2. Well, 2 squared equals 4, minus 3 times 2 is 6, equals 2, which is the absolute value of negative 2 equals 2. And yep, 2 equals 2. All right, so far, both x equals 1 and x equals 2 are solutions. All right, and so now let's change colors and try to figure out this other mess here. Do I want to do this? Do I want to do this? Oh my goodness. You know what? I'm gonna do a little shortcut. I'm not gonna I just don't want to substitute 3 plus root 17 over 2 into the absolute value of x squared minus 3x equals 2. I just don't want to do it. I am lazy. Go ahead and use your graphing calculator if you want to verify that. I'm just feeling a little bit too lazy on this beautiful spring evening to substitute x equals 3 plus or minus root 17 plus 2 into the whole equation, see what I get. But I think there might be another way for us to suss out what's going on. And what I'm going to do is think of it this way. I don't know what root 17 is exactly. It's irrational, but I do know what root 16 is. So root 16 is 4. And so now if we want to just estimate here, we got 3 plus or minus 4 over 2. Well, 3 plus 4 is 7 over 2, about 3.5. And 3 minus 4 is negative 1 over 2, so negative 1/2. So these are some potential x values here. I think I know what's going on with the graph. See if you don't follow along with me here. There's the graph, and let's do the original function here. My parabola, and I don't really know what my parabola is going to look like, but it's going to look something like that. All right. And then once I do the transformation on the parabola, this is going to look the same. That's going to look the same. I'm talking about the absolute value transformation. And then this is going to come up like this, right? And then I've got some value of x that I'm intercepting with. And where does that come from? That comes from here, right? Remember, there's 2 lines here, while 2 curves here. The first curve on the left of the equal sign is a parabola. It's a quadratic. And what is that line x equals 2 going to look like? Well, I don't know, except I know it's going to be up here somewhere, all right? So let's see if we can figure out what these roots mean. Over here, we have roots of 1 and 2. And over here, we have roots of 3.5 and negative 1/2. So I'm willing to bet that this is negative 1/2. And this is not to scale, but it's just, to illustrate a bit of a graphical way of trying to suss this out. I'm willing to bet then that this is 1, that this is 2, and that this is the approximately 3.5. And this is approximately, right? Because we didn't calculate this precisely. So I'm pretty confident that x equals 3 plus or minus root 17 over 2 and 1 and 2 are solutions. So let's just state this and let's put this to sleep. Solutions. And we should probably do them from least to, well, no, I'm going to go 3 plus or minus root 17 over 2 and 1 and 2. And there is my solution set. Time to move on. One more question, and it looks about the same as we've just done. By now, we should be coming pretty cool with figuring out what effect that has on life, the universe, and everything. There are going to be two cases of possible solutions. And because we're dealing with a quadratic, there's actually going to be the potential for up to 4 individual specific real solutions. How do we get there? Well, we get there by stating case 1, which is where x minus 5 equals x squared minus 8x plus 15. And also taking a look then at case 2. And case 2 is going to be where negative x minus 5, in other words, the reciprocal of x minus 5 equals x squared minus 8x plus 15. All right, so there's our two cases, and you'll see that both cases will yield parabolas and quadratics, and so there's a potential for 2 roots in both. We can keep our fingers crossed and hope that they are integrally factorable without using the quadratic formula like the last question, but who knows? We'll only know when we delve into this. If I wanted to simplify case 1, I would probably say that x squared minus 8 minus 1 minus 9x 15 plus 20 equals 0. That would be a good way to simplify that. And that so far is looking good because I identify 2 numbers that multiply to 20 but add to negative 9. And those are the 4, that's 4 and 5, right? So I know I've got a 4 and a 5 in here. I know that they're probably both negative because they have to multiply to give me a positive. So there we go. So there's 2 possible solutions. Zoom pow, love it. If they were not integrally factorable, you know what you'd have to do. In case 1, it seems that x equals 4 or 5. And we probably want to verify that. Do you want to verify it right now? Sure, why not? Okay, let's verify. Let's choose a different color for verifying. All right, verify. Doing this a little bit out of order, but I've got 4 and 5 in my head. So we're going to substitute x equals 4 into the original equation. And when we do so, we're going to get the absolute value of 4 minus 5 equals 4 squared minus 8 times 4 plus 15. All right, so what do we got? We got absolute value of negative 1. That's going to be 1, so let me just put it there. 4 squared is 16. 16 minus 32 plus 15 is going to be equal, well, that looks to be negative 1, doesn't it? Well, you don't have to be a math whiz to know that negative 1 is not equal to positive 1. So x equals 4 is not a solution. All right, well, let's try the next one. Let's try substituting x equals 5 into the original equation 1. Way up here, here's 1. All right, well, what do we got? We have 5 minus 5, the absolute value of 5 minus 5 equals 5 squared minus 8 times 5 plus 15. 5 minus 5 is 0, and the absolute value of 0 is still 0, equals 25 minus 40 plus 15. Well, that looks to be equal to 0, and that looks to be a proper solution. So it looks like x minus 5 is good, x minus 4, not so much. Let's move on to case 2 now. Negative x minus 5, or in other words, the reciprocal of x minus 5 is going to be, and remember what that reciprocal, what that part means. That, this is the regular parabola. Is that the regular parabola? Yeah, that looks like it. Part of the parabola is going to be flipped over, right? And so this reciprocal function, when you multiply -1 by an equation or a function, you get its reciprocal. This is what we're testing for now. So when I simplify case 2, I get -x plus 5 equals x squared minus 8x plus 15. All right. And now let me consolidate my terms all on one side. X squared minus 7x plus 10 equals 0. And okay, I see 2 times 5 making 10, and 2 and 5 making -7. And because this number here, this value is positive, then I know that it's x minus 2, x minus 5. I know that with reasonable certainty, which means that my x values are, or my potential x values, and therefore 2 other potential solutions, are 2 and 5. Cool. Well, the good news here is that we have already done part of our work. We have already tested 5 right here. See? So if I want to verify x equals 5, I've done that already. There it is. All right. So all I really need to do now is verify x equals 2. Substituting x equals 2 back into the original equation, which you'll recall is over there. So we get the absolute value of 2 minus 5 equals x squared. So 2x squared minus 8 times 2 plus 15. And on the left side now, 2 minus 5 is -3 equals 4 minus 16 plus 15. All right, that looks right. Well, absolute value of -3 is 3. And 4 minus 16 plus 15, hey, that's going to equal 3 as well. Cool. Looks like that works as well. So in summation, it looks like out of the 4 possible roots that we have 3 solutions, a 3-solution problem here. So what we've got going on here, I said we had 3 solutions. Well, 2 of the solutions are the same, right? So I think to summarize now, we can say that for x, the solutions are 3 and 5. And 5 hap is the solution to both sides, to both quadratics. So we are good. We are golden. It'd be kind of cool to try to figure out what this looks like. So I invite you to go back to this original here and try to figure out what it looks like.